slightly more interesting. In the next subsection, I want to talk about priority queues, one of the building blocks for many algorithms and data structures, and you will see some examples later in this class as well. So I want to briefly cover these. Also, it was one of the topics that was were half or less than you have seen it before. I want to start off with a little question just to see again how well exactly you know these things. There you go. But I don't really want to wait for your answers at the moment. So the question is about heap ordered trees. This is different from priority queues. The priority queue is really the abstract data type. And I put here this, whatever it is, gin and tonic in the plane. You can sometimes have people with different priorities. You can have business class, first class passengers. And if you're traveling and waiting for boarding at the airport, it might happen that there's not the standard queue where everyone just enters at the end, but some people are allowed to jump the queue and have priority boarding. So this is that explains the picture, just to keep that memorable for you maybe. The priority queue abstract data type is a bag where the items have priorities. And that influences the order in which they are retrieved from the bag. But to be a little more specific, I listed the operations here because we will need some of these for the tutorials as well. We can construct a priority queue from a given number of elements. If they're stored in an array, that's the most convenient way. And you can also start with an empty priority queue and then insert elements with a certain priority. The difference is that the construction from a given set of elements might be cheaper because you can do a bulk insert instead of inserting them one at a time. And we'll see that precisely this happens for binary heaps. Then there's an operation max, like top in the stack. That is just retrieving the item that would be deleted next. So that's the item with the largest priority. And you can delete the maximum, which removes it and also returns it. Sometimes you also need an operation to change a key or to delete an element with a pointer. Well, I won't obsess about this too much. I just want to mention, for those of you who have seen it before, you usually assume that the element whose key you're changing is given to you by a pointer into the data structure. So you somehow keep track of where this is, and you can jump right to that element. That's something that's sometimes not stressed too much in theory classes, but if you implement binary search, binary heaps, and try to do the change key, you need to know where the element is. Maybe this will make more sense in 20 minutes. And we can sometimes do a check for empty, but that's easy. So priority queues turn out to be a fundamental building block for graph algorithms, for coding algorithms that we'll see, and they often simplify how you can specify an algorithm. So they are really fundamental and widely used. Now, a priority queue is really not one ADT, but two, because I specified here everything for maximum, but sometimes it's more convenient to have the minimum instead of max. So same game, it's just flipping everything around. The theoretician would say, wow, you just invert the order. Whenever you have two elements, you define the order that gives exactly the opposite answer. And that's fine, but in practice, you sometimes just want to not confuse the user by using the exact opposite terminology. So both exist, and to make it a little confusing for students, some textbooks use the min-oriented version, some the max one. I used the one max-oriented will be what we use in this unit, because that's what the videos I mentioned on the website also use. So to be consistent with those. All right, I haven't started the other question, so let's first go to that one. And well, we'll do that differently this time. I will just stop the question now. I'll show you the results. But we will come back to this later. So instead, I want to ask this question. If we start with an empty priority queue and insert these numbers and then do a delete min, what happens? I guess you guys were still busy with reading the binary heap answers because they were long and lots of text. Okay, now the answers come along. And to make it a little more challenging, notice I used delete min here. So this is the min-oriented version. Despite what I said, in this unit, we want to use the delete min. This question, the delete max, this question uses the delete min. That was not supposed to be a trick question. Probably should have changed it to delete max, but let's keep it as it is for now. Okay. Yeah, most of you got that right. I got a few people confused with delete max, I think. Of course, it's 1 if this is the natural order. If you insert these elements into the priority queue, delete min will remove the smallest of those and return it, and that's the 1. That's why that's the answer. So that was that. And let's now look at how we can implement priority queues. First of all, we can do very elementary things. We can keep an unordered list of items. Then it's cheap to insert, but for delete max, we have to scan the entire list. Not very interesting. The opposite is we can keep a sorted list. Then we can easily delete the max because it's always at one end. Say you sorted decreasing. So well, this is confusing. Decreasing like that, I'm mirrored. So you have the smallest element at the beginning. But insertion can take linear time because you have to move elements around. I'm assuming it's well, if it's an array, you have to move elements. If it's a linked list, you have to find the insertion position, and you can only do this by walking through the list. So both of these are not really good. But they might be inspiration for looking at the better solutions. The problem here was we went to two extremes, either not sorted at all or completely sorted. Not sorted at all was good for insert, completely sorted was good for delete max. Maybe we want to do something in the middle, slightly sorted. So what's a slightly sorted list? A slightly sorted list is a binary heap. In a way, that's one way to see it. And there's really no good. There's really two ways how you can define a heap. A more intuitive one is the tree view that I will mostly use, but for implementations, there's an array view which is also useful. Let's look at the tree view first, and that comes back to the question I posed at the beginning. A heap is a tree where the shape is restricted to a complete binary tree, and I will usually draw these like this. The reason for that is a complete binary tree means it has full levels, except for maybe the last level. Now this one should be a little closer to that, so that's a left child. that's a complete binary tree. So a heap, in our setting, a binary heap has to have this shape. It's a binary tree, but it has to have this very specific shape. All levels full, and the last level as far to the left as possible. And heap ordered, which means that the keys, whenever I compare two keys, and one is the father of the other, the parent of the other, I should really use the gender neutral version here. Doesn't matter. So if the parent has a key and the child has a key, then the parent key must be bigger. We can store such a key, store such a tree conveniently in an array because it has this very specific shape. And what you do for that is you essentially walk through the tree in this way, level by level. So sometimes called level order traversal. And then you assign indices in the array like so. You start with 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on if the tree was bigger. And then it turns out that magically, if you do that, the array represents a valid heap if and only if for every index we have this condition that the value at this index is smaller, is at most the value of the index where you take I divided by 2 and round down. I suppose you have seen either one of these two conditions, and maybe even both. Both are equivalent in terms of defining things. Usually array view, again, as I said, is for implementing, and the tree view is to make sense of what's happening. So I want to show a concrete example, just so that we're on the same page, what I mean with the heap order. And so here's just a specific example that I made up. And so a few more. And as you can see, it has the shape that I drew before. It's always of this almost complete binary tree. And whenever we follow a path down, say we go like this one, then we always have this is less, that's a bit too fat. This is less, okay, I'm drawing this on like that. Whenever you follow a path from the root down, or wherever you started the tree, if you follow a path downwards in the tree, the keys only get smaller. All right. Let me take a copy of this with me for later, because I will need to draw such trees again. Why do we like exactly this shape? I want to motivate this a little bit before we move on. You will also, I mean, the other answer, one answer to this question would be, that's how it is, and that's how it works. But there's a better answer to that. And I have a couple of reasons here to motivate it a bit. One is there's only one possible tree shape, and that makes life simple. Also, complete binary trees have minimal height among all binary trees, because you put nodes as high up in the tree as possible. So you fill them up in the top part of the tree as long as that's possible, so that they will have minimal height. And we'll see that the operations are essentially bounded by the height of the tree. And last, by fixing this specific shape, we have a very simple formula for embedding nodes in an array. Remember, this level order traversal was giving rise to this very nice formula for the heap property. And similarly, you can navigate from a node to its parent. That's what we used in that formula. You can navigate to the parent by going to the number divided by 2 rounded down. And you can also go in the opposite direction. And why do we like see if I can get out of the way here a bit. Why do we like heap ordered? Well, first, the maximum is always at the root, so the maximum function is trivial to implement. And also, it's sorted along the paths of the tree, but leaves a lot of flexibility in how to assign keys, how to mix the paths in this tree. So it's only very slightly sorted, really, and that will be useful in maintaining this in operations. Okay, so let me just reveal the answers to this old question. No, that was not the one. Sorry, this is the one. So you can see this on the site now, and I like to ask this question precisely because, as you can see, a couple of people mixed it up with the second answer, and that's a typical confusion. Because the two concepts are so similar, it's often that people confuse it with binary search tree properties. We'll come to that. But this is really what heaps are about. Okay. In the remaining time, I want to sketch how you can do operations on binary heaps. So for that, I'll use my little example heap here. Make it a little smaller, and maybe we can get rid of the blue part, which we don't really need. Okay, that takes too long. All right. So here's our binary heap. How can we insert a new element? Say we want to insert the number. What's a nice example? 68, say. Because of the shape, don't want to write this in red. The shape means there's only really one possible position for this new key to go. And that's right here. So we can only really put the 68 here, which means it would connect to this tree like that. Because any other position would violate the shape constraint. So we would rewire this like that. And now we have a problem with the heap property. Because the heap order is violated, potentially, and in this case it is, because 68 is bigger. So what can we do? Well, we take this thing and we modify it. I think I need to make it a little smaller. I hope it's still big enough for you to see. So that was the initial state. Now, we can't really leave it in that state because the heap order is violated here. So we have this problem here. So what we do is we flip those two numbers. Now, I don't know, somehow the gray thing that I drew here nicely is lost. Would have liked this to be like this. Never mind. So we swap those two keys. And try that thereby to repair the heap property. So we let this item 68 swim up the heap. So at this point, we're a little better. This is fine, but here the violation still exists. So we have to continue and do this one more time. one more copy of the tree. And swap those two. So we have 68 here and the 66 from before. And now this is also fine, and this is fine. So at that point, we have reestablished the heap variant, and we're good. This is a valid heap again, and we've inserted this new item. One thing that is important at this stage is, let's see if I can squeeze myself here. While you do this, you swap a larger number up. So this was fine before, and it's also fine afterwards. Whenever you do this, the other children of affected nodes, they're never they will never violate the heap property. So this is never an issue. That was insert. As always, if you have questions, shoot them up. So maybe this is a good time to discuss them. Let me stop the poll now so we can see the questions. Let's see if I made a mistake for the first question. Where am I? Pop this. Yeah, 85 is a 55. I miscopied from my sheet. Thanks for pointing that out. Good, I copied the wrong version 500 times. But no, for the record, let's also fix it up here. And let's copy that one again, even though it means I have to delete the blue part again. Yeah, thanks for pointing that out. For priority queues, would you often plot a graph with items on the x-axis and priorities on the y-axis? I'm not sure what the question hints at. You can do this. It's sometimes insightful. The problem is x might not be a number. It might not be comparable. So the priorities have to be ordered so that you can talk about what is a large priority, what's a small one. The items that we insert in x, they need not be comparable. So sometimes you cannot draw them on the axis. But we will occasionally use that, maybe. Are you saying that the leaf is smaller than the parent? Yes, that's what I'm saying, except that leaf is a special case. Maybe this was the mistake from the slides. Any child is smaller than its parent. That's what I'm saying for the heap property. All right, that was insert. If you have questions to insert, put them in the Q&A. Then the second operation that we want to look at is how to delete the maximum. I promised to stay consistent to the book, so this will be delete maximum, not delete minimum. Let's get my favorite tree here again. Good that I changed this, and let's move these away. And keep hold of it. Now we want to make this smaller, a bit smaller again. Now, deletion of the maximum element. We want to get rid of the biggest element. Finding it is very easy. Of course, the max has to be at the root, so it's right here. And returning that would be easy. The problem now is that we want to delete it. So we store 86 to return it. And now we want to vacate this cell. So we want to get rid of the 87. Now, of course, that's not a good state to be in, because now we don't really have a valid heap. So again, we have to do something. But let me write this down. Finding the max is easy. But when we remove it, we are no longer a complete binary tree. So we have to do something about this. And the only thing we can really do is change the shape of the tree again in the only way that's allowed. And that means taking out this element and moving it up into this gap. So that's what we'll do. The 25 moves up here. This becomes empty, and this is gone. So we're almost good. The heap shape, the tree shape is fine. But the heap property, the heap order, is violated. So we have to do something about this. We have to fix it again. And how do we do this? Well, there's only really one thing we can do. We have to let this element sink down to find a proper place in the heap. That's the term that's usually used. Now, probably need a little more space. So how can we do this? Let's take our favorite tree again. The problem here is that we have two violations. It's violated here and here, but we can only put the 25 down into one of the two slots. Now, which one should we take? If we would swap the 25 with the 66 would still violate the heap condition with the 70, so we can't do this. Instead, we have to compare these two children with each other, and we take the bigger one. So that's the bigger child, so that's the one that we swap. So let's actually do this. Maybe we don't need the red circle anymore here. We put the 70 up here, and we put the 25 down there. Now, by picking the larger child, we make sure that this is fine, and so the whole subtree here is fine. And we made sure this is fine, but we still have a violation here. So we do another round of swapping. And so that you can follow this in the lecture notes, I'll just keep that here. So we swap those two again. Use blue for the swap. So that's the bigger child in this case. So we take that one, swap it with this one, and then you're left with 55 and the 25. And now we have restored the heap property. And that's how you delete the maximum in a heap. Again, any questions, let me know. I know I'm pacing fairly fast through this, but I think if you understand this on the example, you should be able to figure out how this works in general and be able to implement it if necessary. Yeah, as I said, the videos show this in much more detail, and the textbook also has code for this. The last operation I want to discuss is how to construct a heap when we start with a given set of elements. And well, we could do n times insert. But you would, if you analyze this, the total time would be n log n overall time. You have to be a little careful because the insertion takes time log of k for the current size of the heap, and the heap initially is small. But if you look at the last half of the elements, then the heap has already size at least n half, and that's enough to establish the n log n. But we can do better than the n log n. And the idea is to start with small heaps and merge them. So you first start, let's take our, I probably don't have time to go through the full worked example. So you take the last half of your elements and put them as individual numbers here. Then you take the next quarter of your elements and put them above these. Sorry, that's this should be here. And you make these little heaps of size 3. What you have to do for that is let each of these sink down. All right, after you've done that, you have these little heaps. And each of these is a nice little heap. Let me indicate that with the outline. So what I mean by that, each is a true heap in that it has the right shape and it satisfies the heap order. Now you put the next elements up here and do the same thing. You connect these two heaps, pair them up, and again you do a sink for the root. And you do this one more time, and then you have the entire heap. And now, why is this more efficient? You need roughly a quarter times sink in a heap of size 3. At the next step, you would need, for an eighth of the node, sink in a heap of size 7, and so on. This is always a power of 2 minus 1 at most. The last one could be smaller. And here you divide by n to the 2 to the k. Now, if you sum this all up, you will stop when k is log n. And so summing these all up, because most of the insertions of elements are in small heaps, the total cost is linear for this heap construction if you do this bottom-up merging of heaps together. So let me just write that down. And that only leaves to wrap up the binary heaps. I will prepare that for next time so that we save a little time on that. Sorry, you couldn't see that last part. That concludes the construction of heaps, and that concludes the 3 basic operations of a priority queue and how you can do them on binary heaps. You can similarly do the change key operations by letting a node sync up and down depending on how the node, depending on how the weight has changed. And you can do similarly the other operations. But what I've shown you gives you the core picture, and that's how we use that. I'll give the overview slides next time to save time on that.